we have to think of how the agent can make decisions, how the agent can make decisions that lead to it taking the correct action. And so for before going to the formalization of the reinforcement learning problem, just what is the potential of reinforcement learning? What can it achieve? And in this case, one very nice one is OpenAI 5 when it played the game Dota 2, and it was able to play against a professional team, and I believe it won against them. And then there's also Figure AI using reinforcement learning to have this robot operate on its own. And of course, it needs to be trained on so much data for this. Uh, and also there's, stuff like simulation. It doesn't always have to be applicable. It can just be in a simulation, right? A dog walking, a humanoid walking, stumbling. And you can also make them play soccer. But there's also, something that you might know. It's reinforcement learning algorithms are being used in Cursor, which is a platform to uh, boost your coding, I guess. I haven't really played around much with it, but they use reinforcement learning algorithms to learn what users, I guess I believe what users, it sort of learns the trends across, all of its users, users, do they want certain structures in their code, and it's sort of to improve its suggestions to each user. That's what I know, probably. And so now the problem itself is we have an agent in this environment, and we want it to learn, of course, and it's a decision maker. It makes decisions. How it makes these decisions, whether they're informed or malinformed, depends on us, the person who is, making the algorithms for the agent. But effectively in this environment, we give it an action, we give it a state. The agent is in a state. It's going to take an action. It's going to transition to a next state, and it's going to get a reward, and it's going to be in a new state, S apostrophe. And like I said, it's very applicable to your daily life. You can imagine yourself as an agent in whatever environment you have encountered, driving, playing games, in college, right? Your environment is college or your course. You want to achieve the best grade possible, A plus, or even A or A minus, depending on, how hard the course is. But you can imagine yourself as this agent learning, and you're failing, and you're going through all these trials, and you're getting all these different reward signals, whether they're good or bad, high or low. You learn something at the end. And one very important assumption that we're going to be using across the rest of the session is the assumption, the Markov assumption, and it deals with probabilities. And it says that the current state is independent of its history. So as you can see, the green part right there, the probability of being in the next state conditioned on our current state and the state before that and the state before that one. Those other states, those previous states, so we're only focusing on the current state. The previous state, t minus 1, t minus 2, we don't have to look at those. Our current state is independent of those. So we don't need to consider them. So we can just get rid of them. And it's just saying the current state is giving us enough information to make a decision. And the role that this plays is in something, a mathematical structure called a Markov chain, which it's a stochastic process. It's random in that it has probabilities associated with transitioning to each state, whether you go to, I don't know, sunny or you go to cloudy, the probability of going to each of those states is different, and they vary. But it's stochastic in the sense that you don't know if you're going to the next state. You're not certain. Perhaps you will go there, but the probability is, I don't know, 40%, 20%. But there's a chance that you might not transition there at all. So this concept of transitioning between states we can just put into a function, right? I give you a state and I give you an action. So I'm here and I'm going to take an action to the next state. And that's what it's going to give me. It's going to give me the next state, but it's a probability. So perhaps I won't even transition to that next state. The probability might be 0, might be 40%, or even 1. But it's on this notion of uncertainty is very useful to us because the real world is uncertain. We might not know if we're going to wake up tomorrow or in 2 weeks from now, or we might not know if our grade on the next homework assignment is going to be good or bad. And modeling these transitions between states for our agent as uncertain, it just makes sense. And so here's a little diagram. Each of these little cube grids are states. So you would start right there, and you can move around. You can move to the right, you can move to the top, or you can't move to the bottom because there's no probability associated with that. But the probability of going to the left is 1%, right is 1%, and then forward is 80%. And that RS is just the reward. What is the reward associated with the state S? So in this case, S could be this state, it could be that state, it could be any of the other states. And this is our transition model, which associates transitioning from one state to another with some probability that is at least 0 or less than or equal to 1. And so the environment, can we extend this Markov chain to take into account our agent's actions? So could we extend it also to take into account the rewards that we obtain from each state? So this is where it comes in the notion of a Markov decision process, which is just an extension of a Markov chain, which takes into account these transitions and takes into account also the reward. So given an action space, let's say a space of all the actions that are possible, and the state space of all states that we have in our environment, the transition function will just be taking in the current state, the action that the agent takes, and then the next state that it will go to. But of course, it's a probability, so that notion of uncertainty is there. But notice that since it's a probability, we must have that the sum over all of these states in the state space must be equal to 1. Over all the future states, rather, not the current states. And so Markov decision processes are very important. And here's just another diagram. It's a little more, it's similar to the Markov chain that we saw, the little one, but it's just, an extension. And in this case, you have the little red R's, which are the rewards. And of course, we still have the state transition probabilities. But yeah, we still have the rewards there. And the reward can be negative, it can be positive, 0. So every transition that you make, every state that you go to, that you transition to, has an associated reward. And of course, that reward can be good or bad. So trajectories, in this case, will be the sequence of states and actions along the course of however long this your experiment is. And we also call them rollouts or episodes. And so we're starting at some initial state S0, we take some initial action A0, we transition to S1, and then we take another action and so forth. And so all of these states that we're in, all these actions that we take, we just sort of collect them all into a trajectory, which is kind of like our sort of our memory or our experiences that we've had so far. And so if we follow a policy, and we'll look into policies in just a moment, but there's sort of strategies for the agent to follow. And we can improve these policies, we can improve the strategies so that the agent makes better decisions. Better, we haven't defined that. That depends on the problem that you're trying to solve. But we can also include the rewards that we obtain. So at 0, we take action at a 0, and then we get a reward at the next time step. So we have to wait until the next time step, until time equals 1, to get the reward. And so we have to wait until the next time step, so t plus 1. So if we're in t, we have to get the reward in the next time step. And and now we're just putting all of this together. The feedback loop in reinforcement learning, right? We have the environment, we have the agent. The agent will take an action. This action will be sent to the environment. The environment will then provide the agent with a new state and a reward. So the agent is in some state, some current state, it takes an action, and then the environment gives it the new state that it's going to transition to along with the reward. And so that's sort of what the Markov decision process is trying to um, model. And now, what is our goal with transitioning from one state to another state? What are we ultimately trying to do? What do we want the agent to learn? And we need to incentivize the agent with some form of reward, some value. And so that's where the return comes in, which is the total expected sum of rewards over many episodes that we run. And so it's just a sum over the next reward after that. And then we're just trying to quantify what is our expected return. So like what is our expected return on our investment? But one important thing to note is that in the real world, perhaps $10 today will not be the same as $10 in 5 years. So, and also we don't want the agent to go on forever. We want it to, let's say, converge to some optimal goal as fast as possible. We don't want it to take its time. Well, we do, but also we don't want it to go on forever and perhaps it's not going to learn anything in the process. So we introduce a discount rate, which is just going to say that as you accumulate these rewards, we're gonna effectively penalize the rewards as time goes on, and these rewards are gonna decrease. So as you take longer and longer, your reward will become smaller and smaller. So it's gonna tell the agent, or at least nudge the agent to speed up the process. And then policies. So it's a strategy for our agent. How does our agent make decisions? How can our agent make the best decisions? And a policy in this case would just be a mapping from the state to some action. So it's effectively saying what is the probability of taking this action, little a sub t, given that we are in some state right now. And this policy, it could be one of two things. It could be deterministic, it returns one action, or it could be stochastic. It could return a probability of action. So maybe action one has probability 50%, action two has probability 30%, and so on. So we could then choose across this probability distribution of actions which action we want to pick. And generally we deal with stochastic policies because they're just a little more applicable in the real world setting, where taking actions we need to introduce uncertainty in our environment, and to make sure our agent learns to make decisions under uncertain circumstances. And one important concept is then if our agent makes decisions, and let's say our agent has access to a probability of decision of actions that it can take, should it take the action that is most probable or the action that is best for it at the moment, or should it wait for better actions later? And so that's the problem of exploiting what you have access to, the best possible choice at the moment, exploiting that, or exploring and perhaps finding better decisions that you can make. So, an optimal action, perhaps there's better ones out there. So maybe we can take the risk and explore, or we can just keep on doing what we're doing so far. And this whole problem leads to a class of structures called bandits, which are you sort of equip them with some parameter epsilon. Can I explore or exploit? I'm not going to talk about bandits right now, but reinforcement learning further the problem of reinforcement learning has two different settings in which it can be in. The first one, as is natural to most of us, is we're interacting directly with the environment. Uh, but the second one is perhaps we're not interacting directly with the environment. Perhaps it's a little, maybe it's too costly for us, or maybe we don't have direct access to the environment. So perhaps we can sort of log the interactions that we have and store them so that, let's see, it's not direct interaction with the environment. It's just we store the states, we store the actions, and then we sort of, hold on. So this will be better. So that's the one on the top is online. So we gather data by interacting with the environment, and then we sample. So our strategy is a policy, right? And we're going to sample from the current policy. So our strategy, we're going to say, I'm going to pick an action from my current strategy, and I'm going to gain experience. Whether or not this is good or bad experience, right? Do I get good rewards or bad rewards? And then I still need to optimize that policy. We can still do more work on our strategy. We can improve it to later choose better actions. And then the other side of the coin is offline, where we gather data through external experience. Oh yeah, so let's say we don't have access to the environment. We could use uh, a surrogate policy. So a policy, so it's like sampling from a probability distribution. And in this case, the probability distribution will be our policy. And perhaps we can't sample directly from it. So we will sample from something that's easier to access. And in that case will be our external experience. So collecting data, human demonstrations. So like if we're trying to teach a robot how to cook in a kitchen, in a real world kitchen, we could collect videos of people cooking rather than having the robot actually working in the kitchen where it could potentially set things on fire or break something or break itself. We could just collect data externally without having to have that robot interact with the environment directly. So that's another way of a learning under reinforcement learning. And now solving Markov decision processes, there are three main classes of algorithms. The first one is dynamic programming, Monte Carlo methods, and temporal difference learning. But to understand each of these ones, they sort of pile up on each other. So we need to understand the first one before understanding the other ones. We need some tools. We need to equip ourselves with some tools, some way that we can approach these algorithms to solve problems that are formulated under Markov decision processes. And so just a checkpoint where we are right now is we've talked so far about Markov decision processes, right? We have states, we transition between these states, right? This T is just the probability of transitioning to state one, given that we take some action and that we were currently in state one. And then I think that's R, it should be an R, but it should be associated with some reward. So each action takes us to some next state, and then of course these are probabilistic. We are uncertain whether we will actually transition to that next state. So refining decision making, how good is our agent? So for example, our reward signal right now might be looking really nice, but long term, it might actually hurt us, right? So one analogy is, should I for lunch eat fast food or candy, or think about my health long term and perhaps actually ditch the candy, ditch the sugars, and eat something healthier, go to the gym. And so the reward signal is immediate, right? We have an immediate reward signal, but maybe we want to look into long term. We want to make informed decisions. We don't want to just take whatever's there and just be happy with that, right? As individuals, we want to make decisions that are not only best for us, but are also best for us long term. And so there's one function that will sort of describe this. But before introducing that function, we need to have a tool, a mathematical tool, which will allow us to describe over many time steps uh, how good a reward is. So an expectation in this case would just be an average over, in this case, it's a random variable, but it could be an average over the rewards that we obtain over some episode, for some amount of time. It can be continuous, it can be discrete. These are flipped, actually. It should be discrete on the top. It should be continuous on the bottom. But it's just saying what is the expected value that we can get over many iterations of some experiment, right? So like it's mostly used in probability, where we flip dice, we want to say what's the expected number of times. So how many times am I going to flip? How many times am I going to roll six, or two, or one? Or how many times am I going to flip a heads with a fair-sided coin? So that's what expectations are useful for. But in this case, we're going to use them for something that's going to really equip our agent to make better decisions. So right now, so far we have a policy, an agent is going to follow this policy. The policy is effectively a strategy so that the agent can make decisions. So the strategy tells the agent, here's an action, or here's a probability of actions, and you can choose which action might be best for you in the moment or perhaps in the long term. But perhaps we want something that says, how good is this action really, for you in the current moment? And that's what the value function is. It's going to tell the agent, what is the expected value of the discounted return given, so you see that little division, that's not a division, that's a conditioned, so that's GT, where that's the discounted return. So the discounted return, as I said, was back here. That's a discounted return, right? $10 today is not the same as $10 in 5 years. And so that's the discounted return, the sum of all of our rewards, given that we need to, of course, penalize the agent for taking too long, conditioned that we are in a current state. So what is the expected value of the current state? If we stay in this state, what is our expected return on this? Is it good? Is it a good state to be in, or is it a bad state to be in? And if it's a bad state, we need to transition to another state and then check the value of that state. If it's a good state, perhaps we need to stay here and see where it leads us. And so, as you can see, we have S sub t, big S sub t is some ambiguous state. It can be state 0, state 1, state 2. And we can do this for all of our states in the state space. But the terminal state, which is the last state in our episode or rollout, it's always going to be 0. Because at the terminal state, there are no future time steps to look ahead to. So this value function is going to be important because we have a policy, right? What actions can you take? Value function, what action is best for you? So these two things can really help our agent make informed decisions. And so perhaps we want to go a step further. What is the best value function that we can get? That is, what value function is going to be best at predicting how good a state is, right? We don't want a value function that's bad, a value function that tells us, or that's very uncertain, right? A value function that isn't very informative. We want a value function that is informative, a value function that is right all the time, a value function that leads us to some goal, some good reward, the best reward possible. And so we might skip this, but we can derive a recursive equation for this that involves that value function that involves two versions of it, the current version and the next version. So the version at some current time step and the next version at the next time step. So it'll involve those two entities instead of just the current time step. And that's what a recursive equation is. It involves two versions of the same process, just at different time steps. And so we might skip this actually. It's a little, we can look at this later though. It's a little detailed, but we arrive at this actually. So this is what we call a Bellman equation. The rest of the math before you can look at later, but what this is saying is this pi right here is our policy. The policy conditioned on some state S gives us an action, and we're going to take a sum over all of the possible actions, and we're going to collect all of those probabilities, those action probabilities over all possible actions. And then we'll also take another sum over all future states. And this P right there, that little P, says what is the probability of going to the next state, which is S apostrophe, given that we are in some state and that we also take action A in that state. And so we're going to sum over the policy, over the actions, we're going to sum over all the future states. And then also we should be summing over all the rewards, but it's not there. It should be in a little r on the bottom. But then the important thing here is that with the Bellman equation, we can decompose the optimal value function that we can find into two parts, which is the immediate reward at the current time step and the discounted reward of the future state. So like I said, we have the value function evaluated at the current state, but also we also have the value function evaluated at the next state, which is what makes it a recursive equation because we have those two different versions in time of the same function. But it's discounted because we have the discount factor right there, which is between 0 and 1, which we can choose. But it's saying that we can form a relationship between values and future values of our state. And the reason that we have this is because it gives us a nice closed form for finding the optimal value function. So if we want to find the best value function possible, we can just use this equation. Of course, it's gonna, now the thing is though, that it requires complete knowledge of our environment. Why? Because of this right here, this transition probability. We need to have all of those transition probabilities over all future states. And this requires having full knowledge of our environment. And sometimes that may not be possible, but we'll talk about that later. But just keep in mind that this requires full knowledge of our environment for the agent. So this is, of course, putting it into a diagram, right? We have a state, we're going to take an action. It gives us a reward. And then we go to the next state. We also have the policy pi there. But P is just the probability of transitioning between S and S prime, given the action that we take. So that's just a diagram for the value function right there. And V sub pi, what this means is just the value function given that we follow the policy or the strategy pi. So it can be any policy that we have. It can be a terrible policy or a good policy, but it's just a generic policy pi.
We start the calculation from the child.
Yeah, and then we sort of go all the way down. We can have like 100 states or whatever. No, yeah, we need to also wait on that. So of course, since this is a recursive equation, we would start with like a base case. So at time 0, so that'd be like can't really put it into words, but like, am I following the question? Or
And so I will see that the value at state at time t depends on the value of the state at time t. We are calculating that value at time t plus one in order to get our current value at our current.
I think we're gonna use the value here, current value, to calculate this one. And then this would just go on the left, and then we would just keep going until like the terminal time. Does that make sense? Or because we need to calculate that one first and then calculate that one, and then t plus 1 would then be its own equation with t plus 2 and then so on. So does that make? Oh, yeah. Sorry. S dash is the same as st plus 1. It's just, yeah, for,
So, and then we are
yeah, that's pretty much what you can sort of invert it. It's the same if you invert it. Doesn't matter. You're still going from one state to another, so it's gonna branch either way. Uh, yeah, was that your question or? But yeah, sorry, S apostrophe in the P, little p, is the same as st plus 1. It's the next state. And so, we can extend the value function further. The value function currently looks at the expected value of the current state, but we could also take into account the action that we take, given that we're in that state. And that's what the action value function is it also takes into account the action. And it's pretty much the same as the value function. It has the same sum right there. That's the expected discounted return. But this time it's conditioned on both the current state and the action that we take. So it's pretty much the same thing as the value function. It's just taking into account actions. And of course, that might also be a little more expensive to compute, given that we also now have to consider actions. But there's also some important fundamental relations between this and the value function. So there's one that says that the value function, you can find the optimal value function by taking the maximum over all of the action value functions, which is an important result. But you can do many other things with this as well, not just the value function. But then, of course, you have to account for actions. So this is where we are so far, right? Value-based learning, taking what is the value of some state, and this can also include the Q. We call it Q function as well. A Q function, a value function, either one of them are value-based. And this one, right, we give it two actions, so action 0, action 1, from state 1, and that's what we plug into the Q functions. But you don't have to think too much about it. It's just another structure that gives us more power to approach other problems out there. But now we're going to go into the core of Markov decision processes, how we can solve them. The first approach is dynamic programming. And as I said earlier, the Bellman equation required full knowledge of the environment, and this requires full knowledge of the environment. So right here, dynamic programming is effectively, you need to have full knowledge of every single transition probability out there. So a perfect model. And perhaps you might know dynamic programming from, if you're a computer science student, you have to prepare for interviews. So like coding interviews, you have to prepare for dynamic programming problems. And the reason that there's so many of them, perhaps is because, whoever creates these problems, you have to make a perfect model for them to work. And in particular, there's something called an optimal substructure that dynamic programming relies on. Uh, so like optimal substructure would be if you have the optimal solutions to subproblems of a bigger problem, then you can find the optimal solution to the bigger problem, which is what gives dynamic programming all this leverage. But there are three main algorithms under dynamic programming, which are policy evaluation, policy iteration, and value iteration. Policy evaluation should be actually part of iteration policy. So mainly it's just these two right here, policy iteration, value iteration. But what they're trying to achieve is we're trying to improve our policies, right? We're trying to improve our value functions as well. And so first, we're going to look at how can we improve this policy? So it's based on the idea that we have a policy, a random policy, perhaps it's the current policy that we have, the current strategy, and we need to evaluate how good, how successful has this policy been? And then, given this evaluation, perhaps then we could then improve it and then evaluate it again and then improve it. And this is we can go on for as long as we want until we converge to an optimal policy. And so there's two parts to this, of course. There's evaluating the policy. So we need to improve the value estimate. So the value estimate is going to tell us how good what is the value of our states. And so using that, we can then evaluate how good is our policy. And then policy improvement is just going to deal with actually improving that policy given the evaluation that we have. And the evaluation part will improve our value estimate, which we can then use in the second part. And so this is an algorithm of two parts. We're going to take as input some data, which is a threshold. The purpose of this threshold will be to tell us when we converged or not. So let's say it's some very small number, 0.00005. If our policy estimate, so the difference between our policy estimate and the what is the current policy estimate? Yeah, so that threshold comes in the bottom. So like the difference between is that the true value? No, this is the value estimate and this is the true value function. And so we're going to take the difference between those two, and we're going to see if it's less than that threshold. And if it's less than that threshold, then we've already converged. If it's greater than that threshold, we still need to keep running the algorithm. And so we're going to initialize the value function with some state in the real numbers, and then some policy, which is a probability over all actions. And so, as I said, we can find a better policy, but we can do it in a greedy manner. So greedy in this case will be, I will take all the best opportunities that I get at the moment. So it's like someone that's greedy is, taking all the bags of cash. So it's like in this case, greedy being that you're going to take, if you have the best policy in front of you, that's what you're always going to take. You're not going to consider exploring for better policies out there. You're just going to keep exploiting and exploiting. And that's how we're going to improve the policies. We're just going to keep taking the best course of action every time. And it can be described in this little sentence right here. Fully evaluate my strategy or policy and improve it. So in pseudocode, this is what it looks like. So it's a loop, and we're going to initialize our threshold. And then for each state, all states in the state space, it can be a grid, like a grid world. It can be, a robot moving in a little state space. We initialize little v with the current value function, and then we get a new value function estimate using the Bellman equation right here. So that's pretty familiar, the Bellman equation that we just talked about, the current value estimate, the current reward of the value estimate, and then the discounted of the future value estimate. And then the threshold would just be the maximum of the threshold that's here. So in this case, it's 0. So obviously, if this is greater than 0, it will be the maximum. Between the threshold and the difference between the current value estimate and the new estimated value function. So we're just seeing, has it improved? Is it doing better than the previous value estimate? And this is going to tell us, the value of this difference right here will tell us, is it positive, is it negative, or is it 0? Are they the same? Has it not changed? But ideally, we do want the big V of S to change. We don't want it to be the same. We don't want it to even perform worse. We want it to be better. So, and then we run this until we see that this delta threshold is less than the theta that we gave as input to the algorithm. So the theta is the threshold. So we're just seeing if it's less than theta. And then policy improvement would just be improving the policy given that value estimate. So let's say from this part, we got the converged value estimate. So let's say we converged and then we finished this loop because this was less than theta. So now we have that big V of S, which we will then use here to get that new pi. So that pi is a policy, which will just be the maximum over, again, the Bellman equation. But this time it's not a sum over all actions, it's just a sum over the transitions. And the transitions, of course, we need a full knowledge of the environment. And then the ode just stands for the ode policy. And then if the old policy is not equal to the current new policy that we're computing, then it's unstable. We want them to be the same. That means it's a stable algorithm. If it's not, then this becomes false. And if it is false, then we're going to keep on going. If it's stable, that means we have stable updates of our policy. Then we can go back to evaluation, go back to improvement, and so forth. It's a loop until we see that the policy is truly the best one that we can get. So it's like a continuous improvement depending on what we see in the end as fit. If it's good enough, then we'll take it. But what this is trying to tell us is we can always just consider improving, evaluating, improving, just like in the real world. We can just do the same with our grades or with whatever else in our lives, improve and evaluate. And this is sort of a diagram, the little cycle right there. From the policy, we evaluate it, then from the value function, we can then improve it using the value function estimate that we got from the evaluation, improve the policy, and then so forth. And that little thing right there is kind of the relationship that happens. You improve pi to improve the value. It's kind of nice to see that you can improve both at the same time. But the drawback then is, do we really need to fully evaluate the policy each time? What if we can combine the evaluation and the improvement steps? So that's where value iteration comes in. So that's all the way here. Value iteration at the very bottom. It's kind of its little cousin of policy iteration, except that we sort of truncate the evaluation part. We don't do right here, we don't do this full loop. Perhaps we just need to evaluate it once. We just need to take one estimate of the value function just one time. We don't need to do it for every single state. We can just do it once. And that is what value iteration is going to do. It's just, we're going to do that once. So one way to think of it is always act greedily based on our current value estimates. So what that means is the current value estimate in this case would just be evaluating this once, just taking one value estimate, and then taking that with us to the next step. So we don't need to have a value estimate for each and every state in this, we can just have one. So whether or not value iteration converges faster than policy iteration Generally, it doesn't, it's slower, but the purpose is just primarily just taking incremental steps towards improving it rather than, taking full steps and, which naively we might think isn't necessary, but in the real world, experiments have shown that really it doesn't converge as fast or faster than policy iteration. So, but it's still nice to know both of these approaches. But dynamic programming, the main drawback of it is the curse of dimensionality. So as we increase the size of the problem, higher dimensions, it's going to be harder and harder. More computational power is going to be needed, and it's going to take longer to evaluate our algorithms. And that's where it fails. We then need to consider different options. And so the guy on the right, Bellman, he's sort of one of the pioneers of reinforcement learning, and he came up with this this observation that there is a huge drawback in high dimensions of dynamic programming. And yeah, it grows exponentially, which is not good, the number of states. So we need to consider something else. Monte Carlo sampling. So perhaps you've heard of this, perhaps you haven't, but Monte Carlo sampling relies on approximation. So this is very prevalent in reinforcement learning. Approximations are prevalent in reinforcement learning. You can't always compute the exact integral, or you can't always compute the exact expectation of something. So instead, you opt for something approximate. But perhaps the reason that it's most ideal is because it's random. It has some sort of uncertainty in it. So we sample, in this case, we're trying to approximate the value of pi. So, we have all these the blue region is just us sampling different points, but the points are not within the area of the circle. But there's still a chance that we get points within the area of the circle. So there's a chance that we will approximate however long it takes the value of pi, which is like the area under this circle under this curve right here. So it's just repeated random sampling. We don't have any decision in what points are picked. We just know that there's some probability of a point all the way there or all the way within the area that we want. There's some probability of it being picked, but it's pretty much out of our control. But we can, as we see, that 1 over n is the standard notation over n samples. So if we have we want to do, so n right there, we want to do 3,000 samples, 100,000 samples. Then we take, 1 over 3,000, and then sum all the function evaluations for each point. And as we increase n, 100,000, a million, we're going to ultimately converge to whatever structure we're converging to, like integral right there. But it's very important to know. So Monte Carlo methods. So as we saw in dynamic programming, we need full knowledge of the environment. We need full knowledge of every single transition of the Markov decision process and reward. But Monte Carlo methods don't rely on this. We don't need those transition probabilities. As you saw that sum over all the transition probabilities, we don't need that. So instead, we can just follow the policies to generate this episode right here. It's an episode trajectory, whatever you want to call it. State, action, reward, the usual. And then at each time step, we're going to compute this kind of reward. So this is good. But now we're going to hold on this time. Okay. So we have, of course, another recursive equation. We're going to express the policies to the current return using the previous estimates. So gt minus 1, t minus 2 at the previous time steps. So that should be the current one on the left, and that should be the previous ones. but these are discounted. And so using these, we can compute the value. So the way that we derive this recursion just follows from the definition of the return, which is just the sum over discounted rewards. And we can just pull out sum reward. So if it's a sum, we can just pull out terms from the sum and then re-index, and then of course we're gonna have the discount. But it's just like a little algebra that you can do to get that recursion. And then you need to do that for all time steps. But this is what's important, is a value function, of course. But we don't, in reality, we can't always compute the full expectation. We need to approximate again. And this is similar to the Monte Carlo sampling that we saw earlier. But using this, we can then derive a recursive form. So a recursive form using the previous means. So in this case, mean would be just the average, which is the definition right there of the pink mu. So that's one way of computing the expectation. I don't think I covered it, but it's okay. But just then going off of Monte Carlo methods, one thing that we have to we can improve is that we have to wait until the end of the episode to get our return. But perhaps we're impatient. We want to get our estimate as soon as possible. In Monte Carlo methods, we have to wait until the end to get our estimate. But perhaps we can only wait until the next time step to get our estimate, which is the green part right there. So instead of having to wait for the full return over all the rewards that we sum, we can just get the next reward, which is that big R. That's just one scalar value. And then just adding the discounted value of the next state. So that's again, this is just a conservative approach to approximating the value function. And then the alpha right there is a hyperparameter that we can choose as well. But yeah, this is incremental. This is not a full calculation of the return. It's just incremental pieces, just one reward at a time. We're gonna get the immediate rewards instead of waiting the full episode. And then we're gonna use these estimates of the immediate rewards to compute our value function little by little. And so that's what a temporal difference error is. The error in this case is just the difference between this and the current value estimate. And as you can see here, Monte Carlo learning sort of goes all the way down, and it has to compute the full return. You see that half in red right there? You have to go all the way down to compute your return. But here, temporal difference learning, you can just compute the current or the next reward, and you can just little by little make steps in some direction. You don't have to go all the way down. You can just take your time and make little increments. So that's nice to have. You don't have to wait until the end. So that's something that's called bootstrapping. What we're doing here is bootstrapping. We're updating estimates right here based on other estimates. So in this case, updating the value function using other estimates of the value function. So we have many different estimates here, vs sub t plus 1, rather than waiting on the final outcome. So, and then there's another, right there. So we've gone over, so let's go back. So we've gone over dynamic programming, the many approaches of it, policy iteration, value iteration. So let's just have a recap before. So dynamic programming, Monte Carlo methods, temporal difference learning, all of these, unfortunately, I didn't go too much in depth into the last two, but you can solve Markov decision processes with them. And some drawbacks that we considered was full knowledge of the environment. Perhaps we don't need to have that. Perhaps we can, but it's more computationally expensive. but each of them have their ups and downs. Each of them have the scenarios in which they're used. Temporal difference learning is it's used in some very important algorithms. Dynamic programming, it has its use cases. It's very powerful nonetheless because you have that knowledge of the environment. But then there's also something that this whole talk of optimizing policies, optimizing value functions, perhaps we can introduce parameters into this. So if, right, deep learning, all about parameterization, right, tweaking parameters, improving parameters, uh, having all these huge models, these neural networks to tweak the parameters, tweak the weights, and you know, forward pass, backward pass. But yeah, the concept of parameterization can also be applied in reinforcement learning, where we equip the policies with parameters. So like data, we equip some policy with a parameter data, and we want to tweak this parameter. And perhaps that can be a way of optimizing a policy. Instead of having a value function, we can directly equip the policy with a parameter that we can tweak, that we can improve. And these class of methods leads to the intersection of deep learning and reinforcement learning. So like stuff like AlphaGo, AlphaZero use these class of algorithms. So that's you, and then you can climb this mountain right here, policy optimization. But of course, learning all of this is hard. It's difficult. It's a lot of theory. But going back to on policy, off policy RL, I don't think I need to go over this. But just going over that, on policy, you're directly interacting with the environment. Off policy, you have a buffer, some data set that you interact with instead of the environment itself. So as I said, the robot cooking, he doesn't need to actually cook in the kitchen. He can just watch videos, or he can actually cook in the kitchen. So
Policy statement or policy RL
um, so model free in this case would be you need a full model of your environment. So I think that could be for both if you have a full model of your environment. Uh, so you need to have a model to you need to model all of those transitions. So I think it can be both of them. I think you can have, because I think all of those are distinct. So model free, model based, off policy, on policy. I think there's like applications of model based algorithms and off policy as well as on policy, but I'm not sure, but I yeah, I think they're all distinct. I think they're all distinct, but I need to yeah, it's defining all of these is not easy. But just a little glimpse of policy optimization. The probability trajectory tau, so it's a trajectory in episode with t steps, can just be conditioned on our current policy. So it's just saying, following our policy, what is the probability of getting this trajectory of states and actions and rewards? And then we're always going to start in some initial distribution, p sub 0, in some initial state, s sub 0. And then we're just going to multiply by the conditionals, the marginals. So the probability of going to the next state, given the current, and then also the policy. So we're going to have the probability of the next, so the transition probability, and also the policy. So the probability of some action. And then we're going to use this to form an integral, which is like just an average, a continuous average over all of the probability of the trajectory multiplied by the reward. So the reward is going to tell us what is the total reward of this trajectory over all states and actions. And it's just going to take the integral. So it's a continuous entity. And this is actually going to be formulated as a function of the policy. So we're going to give it any function we want. We can give it a good function, a bad function, a good policy, or bad policy. So that's what the function J is going to take. And given the definition of an expectation, this is just the expected value over the trajectory following the policy, the expected return of the trajectory. And in policy optimization, one important structure that we look at is actually the gradient of this J function. So the multi-dimensional derivative of this function, the gradient of this leads to a class of algorithms called policy gradients, but we're not going to go over that. But that's pretty much what it is, just parameterizing. And just tying it back to, because reinforcement learning as it is a field, it can be learning that you can kind of get disconnected from whatever else the world is talking about, like deep learning models and all these language models. But it's making a comeback. Reinforcement learning, not traditional reinforcement learning, but reinforcement learning derived approaches are making their way to language models, and so we can use these approaches to really make our models resemble us, resemble our behaviors, resemble our characteristics. That's what the problem of alignment is aligning our models to our values. And reinforcement learning derived approaches play an important part in deriving these. So that's what reasoning models is the big fad nowadays. And of course, this is the life cycle of a model. I've just building a language model. That's what everything is nowadays, I guess, and foundation model, and then having it for some specific tasks as a classifier, as a personal assistant, a chat bot, whatever. And then the next thing is specialization. But mainly reinforcement learning comes in for reasoning models. That's my lecture right there. You can look at it if you want. It's also pretty dense, but it's pretty nice and informative. But in terms of deep learning, it's not the solution. It's just an extra layer, right? I believe that whatever rich knowledge representations that these language models have, they're just dormant, and we're just taking advantage, or at least aggressively trying to push these models to their full potential. But it's not really solving much. It's just, giving them that nudge that they need. In our case, nudging them towards how we behave, how we want the models to interact with us, right? We want models to be nice, to be caring. And reinforcement learning plays an important role in that and making that possible, right? If you've used ChatGPT, for your homework or anything really, you can see that it's not like toxic, it's not mean or anything. If you want it to be, you can, but I guess. And yeah, reinforcement learning is like the it's the trouble child of machine learning. It's difficult to learn. You need to have a certain mathematical maturity. It's reading it, the slide the first time, you're not gonna, of course, get it. It's a lot to take in. It takes time. But this book right here is like the Bible. So reinforcement learning, Sutton and Bardo. You can find it online for free. But pretty much what I covered today, I wouldn't say it's outdated. It's just you don't you of course, if you want to go further and understand policy gradients as I ended off with here, you don't need to understand everything. You need to go into depth for everything. Like there's a professor at ASU who was one of the pioneers of reinforcement learning, and he actually I'll yeah, and he pretty much dealt with all of this, like even at a more theoretical level, you just equations on equations of theories and proofs and lemmas and theorems, and some may say it's not really applicable if whatever you're pursuing in your career research industry, you don't need to learn all of this theory that the book covers. It's very dense. It's so much material, and the reality is that reinforcement learning approaches don't always work. They almost all the time fail, right? You have to, perhaps there's some parameters that you need to tweak, like by 0.0, 0.1, and it's just trial and error most of the time, and theory doesn't really apply to what actually goes on in your experiments, and so that uh, that misalignment really just uh, keeps people away from reinforcement learning, from actually learning it. And you don't need to know it, but it's definitely nice to know. So I was gonna have code today, but uh, I didn't finish it, and so unfortunately no code. But perhaps next semester I'll actually have like a full notebook that you guys can read through. But yeah, code like what? No, it's far from complete, so I can't really do it. Yeah, sorry, but I guess that's it. So yeah, okay. Learn what? It's or like uh it's definitely, I still, like you saw me, I have some trouble like fully explaining some of the slides. To really, like, I believe that someone like a PhD learner, like explaining each slide in a succinct, I can't do yet. I don't think I will do it in a couple of years, but I guess pretty much it's just me like outside of the class, just reading like articles and the book itself. I don't read the book just like football. Like I just sit down and read the book. I just read it like passages at a time. But mainly my knowledge comes from like articles, blogs, and just like the derivation of learning events and concepts. So like I could solve understanding reasoning models and how reinforcement learning is applied on that. I had that motivation of learning basics of reinforcement learning to then understand how it's used at a higher level. So like in